Dr. Rico here. This is a lecture from my mini course, Robotic Planning and Kinematics. The syllabus and notes are in the description. All right, lecture 7.3, Parametrization of Rotation Matrices, part of the Rotation Matrices chapter. We start with a result on the dimension of the set of special orthogonal matrices, or orthonormal matrices, i.e. on the degrees of freedom of a rotation. Theorem 8.6, Euler rotation theorem. Any rotation matrix in the special orthogonal group 3 can be described by 3 parameters. Proof. A rotation matrix R in this special orthogonal group has 9 entries, okay, as a 3 by 3 matrix does. But each column has unit length. That was the first requirement. So we have restricted ourselves down with 3 constraints. Okay, so each of these columns has to have unit length. And the 3 columns are perpendicular with each other, which is an additional 3 constraints. 3. I keep wanting to say 2. Hence, the degrees of freedom of matrix R are equal to its original 9 entries minus the first 3 constraints minus the second 3 constraints, which gives us 3 degrees of freedom. That was the proof. There are numerous ways to represent R. In what follows, we discuss 1, Euler angles. That's the first one we look at. The second one is roll pitch yaw angles, both very common ways of representing a rotation. And 3, the axis angle parametrization, where we discuss it in terms of a single rotation about an axis that is just the right axis. Okay. And there's a 4th one, unit quaternions, that's mentioned in one of the appendices to this chapter, 7.6.1. I definitely recommend that you check that out. Euler angles. The rotation R is represented by 3 angles, alpha, beta, and gamma, corresponding to basic rotations about the z, y, z axis with respect to successive or body frames. With CB, so we're going to use this cosine and sine being abbreviated as C and S, subscript the angle of their argument. So we have this rotation about the z-axis, successive frame rotation, z, y, z, alpha, beta, gamma being the angles of rotation, and it's equal to this. Okay, if you write out the sine and cosine, it's pretty big, so that's why it gets abbreviated. Equation 7.1, this R above, is illustrated in figure 7.4 with the following convention. So this is the big figure here. 1, rotate x, y, z, 0, about the z0 axis by alpha to obtain x1, y1, z1. So we start off with the x0, y0, z0 frame, and you see them here. So this is the white dot ones, x0, y0, and then z0. And we're going to rotate about the z0 axis alpha. Okay, so alpha is shown here. We're rotating essentially in the plane, because whenever you rotate about one of these axes, there's going to be a plane of rotation. Remember, when you have an axis of rotation, that axis doesn't actually move, right? So in our second frame, 1, the z-axis is the same as the original z-axis. So z1 is equal to z0. But we have a new x1 and a new y1. So a new x-axis, that's x1, and a new y-axis, that's y1. Okay, so that was the first rotation. That was our alpha, first Euler angle. The second rotation is a rotation about the new y-axis, right? Because it's a successive frame rotation, or a body fixed frame rotation. So y1 is our new axis of rotation, and we rotate an angle beta about that axis. So you see that happen in the plane that's more vertically oriented. You see the z1 axis become z2 here, and you see this x1 axis become x2 here, and you see, and of course, y1 and y2 are equal because we're rotating about that axis. Okay, so now we're ready for our third rotation, okay, about z2. So remember, it's z, y, z. So now we're going to rotate about the new z-axis, which is z2, okay? So now we've got z2. Let's locate it here. It's right here. We're going to rotate about this axis. And so this axis won't change when we go to 3. So z2 is equal to z3. So this plane of rotation is this sort of angular plane. You kind of see in gray here. And that rotation is of angle gamma. So we have x2 becoming x3 by rotating gamma, and we have y3 from y2 by rotation gamma. And that is our third Euler angle, our third rotation. So even though the rotation is z, y, z, they're not the same z-axis, right? These are successive frames. So the initial rotation and the final rotation are not a rotation about the same axis. Okay. Inverse kinematics for Euler angles. Equation 7.1, this big one here, boom, states how to compute a rotation matrix from 3 Euler angles. Okay, so how do you get the rotation matrix given alpha, beta, gamma? Next, we consider the following problem. Given a rotation matrix R, compute the Euler angles alpha, beta, gamma, so the inverse. To solve this problem, we carefully consider the 9 scalar equations induced by the matrix equation. So the R rotation matrix is equal to this, and we kind of want to solve it the opposite way, right? We want to solve for alpha, beta, gamma. It's a big nonlinear problem, so hopefully we can do it. We can. But it might take some caveats or some nuance. So from the 3, 3 entry, we start there because look, that only has cosine of beta. Nice, easy one, right? It doesn't have, these all other ones have 2 angles at least. This one has 1 angle. We can set that equal to R3, 3. So we can see this equality, cosine beta equals R3, 3. Recall that we discussed this problem and its solution in equation 3.3, so it should be way back in chapter 3, via the 4-quadrant arctangent function, arctan 2. So arctan 2. So you got to get that 2 in there, otherwise you're going to lose information. So go back and check that out if you'd like. Specifically, for the magnitude of R33 less than 1, then we compute 2 solutions, one with sine beta greater than 0, the other with sine beta less than 0. Since beta is known, it is easy to use again the atan2 function to compute alpha from the entries R13 and R23, and gamma from the entries R31, R32. It's a sort of successive solution problem. Once you've got beta, this equality will help get you gamma. And once you have beta and gamma, then you can find alpha or vice versa. So these arguments lead to the following theorem and algorithm that follows it. So the existence and non-uniqueness of Euler angles. Consider a rotation matrix R with components R, I, J, with I and J being 1, 2, and 3, and the equation 7.1 above in the variables alpha, beta, and gamma. 1. If R33 is between -1 and 1, not inclusive of -1 and 1, then there are 2 sets of Euler angles alpha, beta, gamma solving equation 7.1. If R33 is equal to plus or minus 1, then equation 7.1 admits infinite solutions alpha, beta, gamma. That's actually problematic when that happens. Moreover, the following algorithm computes the Euler angles of any rotation matrix. Okay, so we can use this algorithm, the Euler Angles algorithm, to compute the Euler angles given a rotation matrix. So a rotation matrix R with components R, I, J here. The output is the Euler angles alpha, beta, gamma for rotation matrix R, i.e. the solutions to equation 7.1. And it's a pretty straightforward algorithm. It's just nice to write it out this way. So it gives you all of the formulas you need, and that's in one compact place. So here's how to do what it is actually an inverse kinematics problem, which is to compute the Euler angles given a rotation matrix. Okay, here's an example. In an example 7.2, we considered the frame sigma 1 defined by remember this, we took the new x1 axis, or the new x-axis, call it x1, to be equal to the old or 0 y-axis. So x1 equals y0, y1 equals z0, and z1 equals x0. We got a right-hand 0 reference frame. And then we rotated it, okay? So we did a rotation of it to get our new sigma 1. One can verify that sigma 1 is right-handed and that sigma 1 is not a rotation about a basic axis of sigma 1. So as we did in that problem, we discussed that very shortly. The reference frame rotation matrix is, as we discussed before, given by R10. We wish to compute the Euler angles for this rotation matrix. Okay, we have a rotation matrix. We want to know what are the Euler angles that we need to rotate about. The Euler angle algorithm above leads to the two following solutions. So beta 1, alpha 1, gamma 1. So here are the three Euler angles for this case, and then beta 2, alpha 2, gamma 2. And this is the order in which you might calculate them. But of course, the angles are always alpha, beta, gamma. So I rearranged them after each of these statements. So from the first set of Euler angles, we know and we indeed verify that this is the case. So the rotation about y pi over 2, rotation of z about pi over 2 is equal to R10. So the order of the multiplication here is determined by theorem 7.4 that we introduced above for successive or body frame rotations. So since the Euler angles are using successive reference frames, right? We're using a body fixed reference frame that moves every time you rotate, then you have to use this order of multiplication. The Euler angles are a ZYZ rotation, right? So Z, new Y, new Z rotation. So we rotate about Z 0, we rotate about Y pi over 2, we rotate about Z pi over 2. And this gives us this representation here. So in fact, we got back our original rotation matrix R10 there. So we just did this to check to make sure we got our Euler angles right. So we did the inverse problem. Now we're just going to do a check to make sure that if we go in the forward direction that we indeed get the rotation matrix that we started with. So the same for the other set of angles. So we did the inverse and then we did the forward kinematics just to make sure that we got the right inverse. Roll pitch yaw angles. We're not going to go as deeply into this, but we consider a second parametrization. The rotation R is represented by three angles, alpha, beta, gamma, corresponding to basic rotations about X, Y, Z axes with respect to fixed frame. So Z, Y, X, X, Y, Z, alpha, beta, gamma. It's a fixed reference frame rotation. These angles are illustrated in 7.5, figure 7.5. The remaining analysis is similar to that for the Euler angles. Roll, pitch, yaw conventions for the aircraft are given here. We've already talked about roll, pitch, and yaw, so nothing surprising here. Assume a rotating frame or a body fixed frame or a successive frame is attached to a vehicle. The axes are set as follows. The x-axis points forward, roll axis in a boat, and the z-axis points downward towards Earth in an aircraft. Then alpha about x-axis is the roll angle, beta about the y-axis is the pitch angle, gamma about the z-axis is the yaw angle. We do not discuss here the inverse kinematics for the roll, pitch, yaw angles as we did earlier for the Euler angles. Instead, we refer the reader to the exercise 7.7 for more fun. Axis angle parametrization. In this subsection, we discuss the axis angle parametrization. We answer two questions. One, what is the rotation matrix corresponding to a given rotation, axis, and angle? And two, what are the rotation, axis, and angle of a given rotation matrix? This second question is well posed because it is true that each rotation is necessarily a rotation about an axis. Okay? You might not know which axis it is, but every rotation is a rotation about an axis. Preliminaries. skewsymmetric matrices. Okay, got to kind of learn a little bit of this mathematics before we can tackle this. We begin with a necessary detour into the world of three-dimensional skewsymmetric matrices. Definition 8.9 of a skewsymmetric matrix. A square matrix is skewsymmetric when it is equal to minus its transpose. The set of three-dimensional skewsymmetric matrices has a specific symbol. It looks like the special orthogonal group SO3, but it's lowercase. Okay, SO3 is equal to the set of matrices, 3x3 matrices, such that the transpose of the matrix is equal to the negative of the matrix. Okay. In skewsymmetric matrices, the diagonal entries are always 0. Why does that have to be the case? Think about it for a minute. Think about the diagonal in particular. And the lower diagonal elements are uniquely determined by the upper diagonal elements. In other words, given an incomplete matrix with A, B, and C filled in, these stars representing just any other elements, there is a unique way of completing it if it is skewsymmetric. So if this matrix that you're given, which has A, B, and C in it, is skewsymmetric, you know what all the stars have to be. The diagonal has to be 0, and it has to have the negative transpose elements in the lower triangle. In other words, 3x3 skew matrices have 3 degrees of freedom. There are 3 entries that you can determine. The rest of them are determined from those 3. Next, we set up an equivalence between SO3 and R3. Given 3 real numbers, omega 1, omega 2, and omega 3, we define the operation hat here from R3 to SO3, and its inverse, could call it cup, maybe cup, hat and cup, by hat on omega 1, omega 2, and omega 3 is just the construction of a specific skewsymmetric matrix. Okay, so once we set negative omega 1 here, this guy down here was required. It had to be omega 1. We set omega 2 here, negative, omega 2 had to be determined. Set omega 3 here, negative, had to be positive over here. Zeros along the diagonal. And so what we do is we take this vector and we form a skewsymmetric matrix from it. Now we have the other operation here, which is cup, where we take a skewsymmetric matrix and we have a vector pop out of it that corresponds to that skewsymmetric matrix. Okay. The inverse is this. This is the forward version of this operation. A few additional properties of skewsymmetric matrices are given in section 7.4. It's an appendix. The axis angle parametrization and its inverse. We are now ready to consider the following problem now that we've got the hat and the cup operators. Given a unit length rotation axis and angle, what is the corresponding rotation matrix? Here's Rodriguez's formula, which is an important formula. Given a unit length rotation axis n, okay, so it could be anything, right? An axis is just a unit vector pointing in some direction. And angle theta, there exists a unique rotation matrix denoted by rotation sub n, so rotation about axis n of angle theta, representing a rotation about n by angle theta, and is given by equation 7.3. So we have the rotation about n theta equal to the identity matrix, the 3x3 identity matrix, plus sine theta times n hat. Now n is a vector, n hat we just defined up here to be this skewsymmetric matrix formed from the entries of that vector. So it's a skewsymmetric matrix, and times sine theta, a scalar, plus 1 minus cosine theta, so another scalar, times n hat squared. Squaring a matrix is fine. You just multiply it by itself. As long as it's a square matrix, you can square it without any trouble. So that's what we've got. It is a simple exercise to check that the matrix rotation about n of angle theta, as defined in equation 7.3 here, is indeed a rotation matrix in the special orthonormal group 3. We postpone the proof of this formula to the section 7.5 in an appendix. It's called Rodriguez's formula proof, or proof of Rodriguez's formula and of its inverse. But you can check that out. Note that for small angles theta, the formula is approximately this, which is to say the small angle approximation tells us that sine theta is approximately equal to theta, and cosine theta is approximately equal to 1. 1 minus 1 is 0, so this term goes away, and we get this approximation. And it can be interpreted as a first-order Taylor series expansion. Okay, example 811. For example, consider theta equals 2 pi over 3 and n equals this normalized vector in the 1, 1, 1 direction, okay? Note easily that sine theta is equal to root 3 over 2 and cosine theta is equal to negative 1/2. We take the skewsymmetric operator on the n-axis and we construct the skewsymmetric matrix. We square it to get this. Therefore, we're just computing it with the formula, plug it in, and we get this rotation about axis n of theta. The rotation matrix is here. Next, we are also interested in the inverse kinematics problem. Given a rotation matrix R, what is the rotation angle theta and the corresponding axis of rotation n? Inverse Rodriguez formula. Given an arbitrary rotation matrix R, consider the Rodriguez formula, equation 7.3, in the two variables theta and n, where theta is the angle of rotation in 0 to pi, and n is the unit length axis of rotation. 1. If R is the identity matrix, then there exists an infinite number of solutions defined by theta equals 0 and any old axis you like. 2. If the trace of R is the sum of its diagonal elements, right, is between 3 and -1, so between -1 and 3, then there exists a unique solution defined by these two equations where we've used that cup here. We're going to take that skewsymmetric matrix, we're going to convert that into a vector, a unit length vector that defines the axis n within a factor 1 over 2 sine theta. If the trace of R is equal to -1, then there exist two solutions defined by theta equals pi, and by the two solutions n1 equals -n2, and n transpose is equal to this. Okay, so let's take a look at this inverse problem in an example. As before, we consider the frame sigma 1 defined by this whole swapping x and y axes around with the reference frame rotation matrix that we've looked at a few times now. We now wish to compute the rotation axis and angle for this rotation matrix. Using the inverse Rodriguez formula and equation 7.2, we obtain this. Theta is equal to this, which is just generally true, and we can compute it for a given rotation matrix to find what theta is. It's 2 pi over 3. N is equal to this formula, like we saw above, and if you compute this, you get this skewsymmetric matrix. The skewsymmetric matrix is turned into an axis or into a vector via this cup operator, and we are left with the axis of rotation. So it's kind of nice because if you rotate the x, y, and z axes, then you end up rotating about an axis that's in the 1, 1, 1 direction. So you can imagine that this axis is not in the direction of any of these axes in particular, but extending out in the 1, 1, 1 direction. And then of course you have to normalize that. Okay, so that is it for the Rodriguez formula and the inverse Rodriguez formula. Also, the parametrizations of rotation matrices are finished up. There are several appendices to this chapter, and I highly recommend that you read through them, especially the one on quaternions. But I'm not going to be doing any videos for those, so you're going to have to just read those, and you're going to be okay. So, all right, I'll see you next time in chapter 8. Take care.